Dr. Rabin Bhattarai is an associate professor of soil and water resources engineering in the Department of Agricultural and Biological Engineering at the University of Illinois Urbana-Champaign campus. The overall goal of his research group is to develop sustainable engineering solutions to improve water quality and crop production. Along with conducting experimental studies, his group also uses computer simulation models to predict water quality and crop production at various scales. The past and ongoing research projects in his research group are supported by multiple agencies, including the United States Department of Agriculture, Illinois NREC, and the Illinois Department of Transportation. And it's my pleasure to hand it over to Dr. Rabin Bhattarai.
Thank you, Julie, for that introduction. And I have been actually given a tough job of keeping you guys awake after that good lunch. And I'll try my best to keep you awake and see how that goes. So first of all, thank you, NREC, actually, to providing the funding to do this research that we have been doing, this experimental study in our university farm for the last 4 years. We just completed experiment last year, and I'm going to share some of the results that we have found during the study. So first, probably all of you know what tile drainage is, why it's important, especially for this reason where we are in a topography and in a formation like where we have very flat terrain and water moves very slowly in our soils, where water can easily accumulate on your surface. And also we have this shallow groundwater table. So subsurface drainage or tile drainage that we know, it helps valuable solution for enhancing crop productivity in poorly drained soil that we have majority of our central and northern part of the state, and as well as our neighboring state. So that helps not only draining your soil faster, but as the picture shows, also bringing down your water table at a desirable level so that crop can thrive and get good yield out of those poorly drained soil. And then it helps also prevent situations like this, like you're getting stuck in the field when your field is too wet. And if you look at how prevalent this practice is, as you can, this diagram shows coming out from National Census of Agriculture a few years ago. It shows it's very common practice, especially in the upper Midwest, upper Mississippi River Basin, northern central Illinois, Indiana, Ohio, Michigan, even Iowa, and some part of even Dakotas. And it's always common practice in the region, also associated with actually issues like water quality problem, because as your water moves through the tile, it also takes a lot of nutrient from those soil, especially soluble nitrate. And that has been creating a lot of issue in our stream and rivers, not in the state also, but also going that where the water ends up, like Ohio River or Illinois River, ultimately to Mississippi and Gulf of Mexico, and then creates this big hypoxic zone every summer. And I think the largest ever measure was in just a few years ago, not that far, in 2017. That was, the hypoxic zone was around like 8,700 square mile. And we have seen other big similar situation, like I think the other one was in 2019, where we had around like almost more than 7,000 square mile of hypoxic zone that summer, and 21 again, around 6,500 square mile, and which is way above like the target that we wanted to keep. In that, our Gulf of Mexico Hypoxic Task Force has the target of keeping that below 2,000 square mile, but last few years have been probably, I think, the other spectrum, like we have seen some of the largest hypoxic zone in the region in the last few years, like 17, 19, 21, and that is a lot of reason, right? It's not only the your agricultural practices, but also sometimes in Mother Nature. Sometimes when you have wet spring, that drains a lot of field, and when you have, especially spring has to be warmer as well, when there are a lot of microbial activities can happen, and that can liberate a lot of your nitrate from the field. We have no control over that. So it's basically what we are doing in the field versus what Mother Nature is also doing at the same time can make issue even worse. So what we are doing in this study then was looking at the tile drainage is commonly used practice. To grow our crops, if you want a good yield, probably you need tile drainage, especially you are using any like poorly drained soil like Drummer, Flanagan, like Kathleen, silt loam, things like that, okay? So, and then the problem with the tile drainage sometimes is actually we don't know what is the sweet spot, because we need soil drainage for good yield, but then drainage also can reduce, leach a lot of nutrient then, right? It ends up in your drainage ditch and ultimately to Mississippi and creating this hypoxic zone. So can we find the sweet spot? Like, can we design the drainage in such a way that we can get good yield still, but we can minimize the loss? So that was the basic premise of this study. And then we looked at past studies. We looked at how the drainage design, especially like two aspects of drainage design, right? How far you want to put the tile lines and how deep you want to put the tile lines, spacing and depth, okay? And how that impacts. Like a past study have shown that, for example, closer you put tile lines, you lose more water and probably more nitrate. But then this spacing and depth is also like actually in a sense your combination affects how you manage the groundwater table in the field, right? Because if you're too far apart, then your groundwater table will go too down from your soil level, okay? So it's basically how deep and how far affects how you are managing the groundwater table in the field as well, so that impacts your crop production. So for this study, as funded by NREC a few years ago, we were looking at how does the different spacing and depth combination affects the nitrate loss as well as crop yield in our system. So this is the study conducted in our university research farm, in the South Farm, where we looked at three combinations of the spacing and depth, and we have replication, because we wanted to see, can we see the result replicated? That means what one combination is saying the same one. So we had this 30-acre field, so we divided that into 6 different. So as you can see, a combination here. So we had, each field had around like a 5-acre area. So CS1 and CS3, okay, this in a pair, they had around 40 feet spacing and 3.5 feet depth. So we put the tile on those combination. And for CS2 and CS4 field, we put them exactly like double the spacing. So they were 80 feet apart and 3.5 feet depth. And then for CS5 and CS6 field, we put tile spacing at 60 feet, and our depth was 2.5, okay? And we wanted to see then how does this affects, okay? Like having 3 combinations. So one was 40 versus 80, just double the spacing, and other one was actually between your 83.5 and 63.5 was actually having the same, we call it drainage coefficient. So that means the maximum amount of water we can drain in 24 hours, like how much water we can drain. So these two combination, either you put 83.5 or 62.5, you are having the same drainage coefficient in that case, okay? And this is our soil map for the field, as you can see. So majority of the field was in Drummer. Almost 50% of the field was Drummer soil, 40% was a Flanagan. So you have your Drummer silty clay loam, our state soil, Flanagan silt loam. We had some patch like around 15% of your Kathleen silt loam here on your southeast corner of the field. We have on small patches of your Thorpe silt loam, Elburn silt loam, and Sawmill silt clay loam in this field. So this is our soil map. In terms of soil property, not that big a difference, okay, except like this combination of your silty clay loam and silt loam. So the first thing we looked at actually is then, how does the water dynamics is different in this 6 field year to year? So we actually put this tile in this field in 18 spring. And then we started collecting the data that summer, but then we saw like the field was still settling, and then we saw like there were some results were not, I would say like satisfactory or reasonable. Then we thought maybe wait. We started actually the actual, and we still instrumenting the site. We're putting the control structure and all those things that summer, and we finally started collecting the actual data set from that fall. 18 fall. And then we did that for 4 years, 18 through 22 crop years. So here is the first result we have is your water balance in the fields. How does water differs in terms of your partitions among like annual rainfall, your ET, and surface drainage flow from this field. Okay, as you can see, there was some variation among the response. Like for example, if you look at these are the field where we are planting corn, soybean year by year, so that means almost half of the water actually we lose through ET, as you can see. And these were ET estimate was from measured ET provided by Morris satellite. Okay. And then we looked at individual field response. So these are year-by-year results. As you can see, this is like for year 1 was October 18 through September 19, so we follow the water year. Dynamics here, and these are 6 field numbers. So these are your year 1, year 2, year 3, year 4. What we found out actually is that in terms of average, we found out the highest average tile flow was recorded in the CS1, which has 40 and 3.5 feet, your depth spacing result. And lowest was from CS6, which was your 60 and 2.5. And then what we found out actually is that between all these years, we looked at and around like, when we look at the water balance, the tile flow was around like 40% of the total rainfall on average from this all 6 plot throughout the 4 years of study period. And then this diagram shows you the variation in the tile flow response between the different your plot. As you can see, like your CS1 and CS2, which had 40 feet, which is narrower spacing. Okay, obviously that we're expecting narrower spacing, probably that will have more tile flow, which our studies kind of verified. Okay, so your CS1 and CS3 had the highest tile flow among these 3 combinations, followed by your CS 2 and 4, 80 and 3.5, which were the red lines. And then we saw a big discrepancy in actually the third combination, 5 and 6. And we saw like CS5 was narrowly following the trend in 3 and 4. However, CS6 was standing alone on the bottom of this chart. And we are wondering actually what happened. If 1 and 3 are kind of same, okay, the response of these two with the same spacing and depth is same, but then again, because 1-3 has narrower spacing compared to 2-4, we are obviously will getting more tile loss, water loss from the tile, but then why like the response, and then again, your 2-4 has the similar response, but why 5-6 had a big change in this response. So we thought about like, what about like, let's go and check what can be the reason, because the water flow is again, it's hydrology, right? Like what can be effect? So we went back and looked at actually is then how the topography of our field looks like, okay? So this shows you actually the elevation change in our study plot. As you can see, like your bluish region is the highest point of your field, and then green are your middle, and then your red, and your deeper the red becomes that lower spot in the field, okay? So we found that actually then between the 5 and 6, there was significant difference in elevation as well as average slope of the field, okay? Like, 6 is the highest part of the field and had the higher slope compared to other field, and that's what we thought was, and we also actually wanted to look at the flow pattern, surface flow pattern, how the flow will happen. If you have a big rainfall event, where the water will move in the surface as well. And we can see the flow pattern, 6 probably will drain into like a 4, and 4 will go to the 3, and then 3 and 2 combined will do 1, and then part of the 5 will either go into 1 or 5 will drain into your ditch, which is on this side of the field. So we found out actually then the response difference between 5 and 6 due to actually this topography. So most of the time what we thought is not only the tile design, not only how you come up with the depth and spacing, but then where are those fields located in the landscape also matters in terms of how much water you lose and how much tile nitrate you can lose from those fields. And then we also looked at actually then whether those differences, as you can see like here, like there was a line, there were some differences in the response, and we wanted to see whether those responses in terms of this different plot with a similar combination or different combination were significant or statistically. So we ran some statistics to see whether those differences were significant or not. Okay, so what we found out actually is then like your combination of that we had between 1 and 3 was not significantly different, even though there was some difference between your total tile flow over the 4 years. There was some almost 10 centimeter difference, but statistically when you look at when we calculated based on average daily tile flow from this field. They were not. 1 and 3 were significantly different. Similarly, 2 and 4 were different. But 5 and 6, there was some. They were different, significantly different in terms of response, as we saw, like because they behaved very differently in terms of how your tile flow happened on those fields. Okay. And after doing the water part analysis, then we thought, like, okay, how about let's look at the nitrate part? What's happening in those fields in terms of nitrate response? Whether the nitrate response was similar to water response or not. And we found out actually that nitrates even more sometimes get complicated. It's not straightforward that more water you lose is straightforward saying more nitrate you lose. That may not be true as well. So what we see in this graph probably is hard to see. These are, you have to see the 6 figures. Individuals showing your nitrate concentration on those dots. Okay, it's hard to see probably. And in the line showing you actually the nitrate loss on a daily scale, okay, on those lines. And what we found out actually, again, you can see there are some shaded versus non-shaded region. We also wanted to differentiate between this field response between growing season versus non-growing season, okay? The way we differentiated between growing versus non-growing was, okay, if there's something growing in between, let's say most of the time, I think we took May 15 through October 15, there's either corn or soybean in the field, that's our growing season, and October 15 through May 15, we said non-growing season. And we also wanted to see whether the field response was different between growing versus non-growing season. And here we can see also in terms of nitrate, you can see like this in 2019 from CS1, we had actually, this was, I believe, if I recall correctly, this was warm, wet spring that we saw, like there was even like growing season early May, there was increase in the nitrate concentration in the tile flow that year. And we saw like also like many times your nitrate loss was, I think, like high in that late spring first few event. And you can see also the difference in terms of your concentration were not like consistent across the field as well. There was some difference in concentration. Like you can see, for example, like your CS4, this 19-year, as we were progressing towards cropping season, nitrate concentration started to go up, probably because of your warm, wet spring that year we had. And what we did was next was like looking at the daily time scale, but whatever the annual time scale the nitrate loss looks like. Okay, so this table shows you is then the summary of your nitrate loss in kilogram per hectare from those fields. Okay, so as you can see, like for the first year, there were some differences. Like for example, we had highest loss from CS3 and followed by CS4 and then CS1 and then lowest was CS6 as we expected. CS6 was like most of the time. The response of CS6 was pretty sporadic. Like if it rained, the tile started to flow, and after some time it will stop flowing again because of, I think, the way your topography was, the field was, okay? And again, the response was a little different, like as you go from year to year. For example, year 2, we saw that, like, again, CS3 had the highest average tile loss. Again, CS6 has smallest one, okay? And so there was some variation also in terms of like how much your total tile nitrate loss happened from those fields across this cropping season in the 4 different years. And then we also did that cumulative loss as well. We wanted to see like, okay, what happened, not only year to year, but then if you pile up that nitrate loss that happened on daily basis over the years, for the 4 years, then we went to see how the response was, okay? So again, CS3, which 40 by with your 40 feet spacing and 3.5 feet depth, still had the highest loss, and followed by actually another cousin of this one, CS1, which had same combination. But then we also saw actually CS4 also picked it up in the later year, and also like some year actually CS4 had highest, and we actually went to look back why that happened, okay? So what we found out for CS4 was, for some reason, the concentration at CS4 was a little bit consistently higher than other fields for most of the time, and we actually wanted to look at that also. So that means sometimes the nitrate dynamics can be even more complex than the water dynamics. Water dynamics is, I would say, like more straightforward because we have understood hydrology way better than the nitrogen dynamics can happen in the soil when you have this complex interaction between what's happening with the soil organic matter, soil microbe itself, your weather, like your soil moisture, your temperature, your fertilizer input, what kind of fertilizer we applied, whether it's a fall versus spring fertilizer, and when the crop was planted, and all those things, and again your groundwater dynamics, when how much groundwater is at what level at that particular time of the year. All those things does matter when you actually look at nitrate loss from the field. So it's like, and then you can see, like, even though like our highest loss happened through CS1 and lowest happened through your CS6, what happened in the tile flow, but in between other plots, the nitrogen dynamics was not straightforward like what we saw in the other tile flow case in the earlier diagram. And we also wanted to look at actually is then the differences between the plots, and where they were significantly different from each other or not, and few were not, okay? As you can see, this was again a statistical test. We ran this test based on, we calculated daily load for individual plot, and then we run this, we call Tukey test, and the pair test to see whether the difference was significant or not, okay? And we can see, like, for example, 5 and 6 is always significantly different, okay? Whereas others were not. Like, for example, I think 1 and 3 were not, and 2 and 4 were not in that case either. Then we also looked at actually is there any difference in the soil nitrate level also? Because we wanted to see, like, if because of as we see, the response was different in terms of drainage, in terms of soil nitrate, but in terms of nitrate in the tile. We also wanted to see whether there's some variability in the soil nitrate in the field as well. So we did this soil analysis for 2 years, 21 and 22, spring before fertilizer was applied. And we went to the east plot. We took I think we followed NRC's soil analysis guideline. We went to a one point and around like took like 20 random point at 2 different depths, and we composite the sample and analyzed for soil nitrate. And we found that there was some discrepancy. There were some differences in the soil nitrate level. But I would say, like, it was not that a bigger difference. And again, we had just 2 data points, right? Every year at 2 depths. One is 0 to 6 inch, and 6 to 12 inch. You can see those are your 0 to 6 inch is in solid circle versus your 6 to 12 is in dotted circle, and your black line is for 21 and your red line for 22. And we see, like, there was some discrepancy. For example, for your CS6, we had, CS5, we had like a little bit higher compared to the other field. Like CS1 had smaller level, but then you can see still those were not that significantly, I would say, like big of a difference. And we saw that year-to-year variation was not that great either. Like the circle were superimposing pretty well. Okay. And other aspect we wanted to also look at was then how about the crop response? Where was there any difference in the yield? Okay. And again, yield was a variable, okay? Like we saw, like, for example, what happened was we was trying to monitor yield every year, but then unfortunately in the, I think, year 2019, our yield monitor actually broke, right? During the harvest season, and then we didn't have the data, but then we at least collected the year before data, 18, which all field was already tiled. So we looked at 18, 20, and 22 was corn year versus 21 was soybean year. And you can see the differences in yield. For example, for 18, that's your first year right after the tiling was done that spring, we had CS4 and CS6, and CS3 had a little higher yield compared to, let's say, CS1 was on the lower side. And then for other years, for some reason, CS1 yield was significantly lower compared to other fields. And for soybean, they were really comparable, except like a CS2 had in 5,000, whereas other were in high 4,000s. And we can look at the average as well, and we can saw that, like, compared to what we did was the average, this 4 years of corn yield, when out of 4 years, 3 years were corn and 1 year were soybean. The CS1 and CS3 combination, which was our closure spacing, had a little bit smaller, I would say, I don't know, because of the data set, I would not say statistically significant because we just had 4 data points, but our CS1 and CS3 combination had smaller, I think it's like almost 3% and 5% average less yield than actually our CS2, CS4 versus CS5, CS6 combination. So that's what it is then, but having your closer spacing, not only you lose more water and the nitrate, but that can also give a little bit of slight smaller yield compared to the wider your tile spacing. And then other aspect of this project was to actually also kind of extrapolate this result to the other condition, right? For example, we did this study for like just 3 possible spacing depth combination, right? But how about other combinations and other soil conditions? So what we wanted to do, we still this ongoing is try to use this data set from this field to calibrate and validate a field scale field scale water quality model, and then run that model once we have the good handle of this local condition. Now, when we model gives a satisfactory result, run the model for other combinations like, okay, how about like your 50 feet and 3 feet depth, or like other combination that we did not implement in the field, okay? How about those conditions? What happens to the nitrate loss and your tile nitrate loss in those cases, and crop yield as well? So we did one, just a study came earlier last year about just looking at the sensitivity of the model parameters to our data set. And also this part of the project, we also did some actually tools for farmers to design the tile drainage system itself. So this work was done by my collaborator, Dr. Richard Cook, who is Scopia in this project. What he did was they develop a plugin for QGIS, which you can use to then if you bring the LiDAR or your topography per field, it can help you to contour from the map, and then also can give you like the flow lines and the potential tile your spacing depth, and then they have put that whole thing in this link there in their website, in drainage tool in the Illinois Drainage Guide. And last but not least, I want to acknowledge the support provided by my collaborators, my student, my technicians, and big thanks to NREC for supporting this study to get some of the results that I'm sharing with you. It was possible by their generous support and help. With that, I conclude my talk, and I'll be happy to answer any question you have.